Okay, folks, so that should be full screen now. Yeah, can you all see that?
Yeah.
Let's just move that screen back for me. Let's get some close. Right, so the first thing we're going to do, what we're going to do today, is just look at some basic properties of molecules and molecules in solution. Simple things like molecular weight and molar mass. Again, some of this should be very familiar. Macromolecules. Macro is a Greek word meaning large, so large molecules, proteins, polysaccharides, and glycopolymers. These are molecules which have sugar conjugated to them, and nucleic acids fall under that category. Then we're going to look at units and ask ourselves the question why people working on macromolecules, large molecules, often use what's called the CGS system, centimeter gram second, which is not the same as the SI system, which is kilograms meters seconds. And then the free energy equation. And then we'll look at macromolecular shape. So that's the plan for this morning. Right, molecular weight or molecular mass. I don't like the word molecular mass because molecular mass means the mass of a molecule, which is going to be very, very tiny because molecules are very small. What we generally mean by molecular weight or molecular mass is the mass of a molecule compared with the mass of a hydrogen atom. So helium would be 2 because it's got double the molecular mass or molecular weight of a hydrogen atom. It's either got no unit or we give it the unit of Daltons. So Dalton is what people describe molecular weight or molecular mass in. So water, 18, hemoglobin, 64,000 Daltons or 18 Daltons for water. Now, molar mass is the mass in grams or kilograms of 1 mole of molecules, where 1 mole is 6.022 times 10 to the power 23 molecules. Does anyone know what this number is called?
Something constant. Can you remember the name? Avogadro or something.
That's right, Avogadro's number. Yep. So it's the mass in gram or kilogram of 1 mole of molecules, where 1 mole is 6.022 times 10 to the power 23 molecules. So both molecular weight or molecular mass and molar mass in grams per mole are numerically equivalent, and we give it the symbol M. So the molar mass is the mass, gram or kilogram, of 1 mole of molecules, where 1 mole is not 1 molecule, but this number of molecules. This number of molecules in a mole. So both molecular weight and molar mass are numerically equivalent and have the symbol M. Molar mass in gram per mole. So water has a molecular weight of 18 Daltons. It has a molar mass of 18 grams per mole. that means this number of water molecules weighs 18 grams. So molecular weight and molar mass we use interchangeably, particularly if molar mass is in grams per mole. Okay, folks, is that understood?
Mm-hmm.
So you can see me on this board. Can you see me, folks?
Yes. Yeah.
So 18 daltons is 18 grams per mole. That's H2O. Okay, can you see that?
Yeah. Like not very clear, but yeah.
Let's bring this a bit nearer. Okay, how about that? Yeah. Right. Okay. Let's move on. So that's molecular weight and molar mass, and we're going to be talking about generally large molecules, and these large molecules, macromolecules, are normally molecules whose molecular weight is larger than 1,000 or 2,000 gram per mole or Dalton. So water is not a macromolecule; it's a small molecule, but a protein like hemoglobin is a macromolecule. It's got a molecular weight of 64,000 Daltons, or molar mass 64,000 gram per mole. So that would be a macromolecule. So let's take proteins first of all. Let's take an amino acid. An amino acid has, well, molecular weight depends on the side chain really, but a typical molecular weight for an amino acid is about 100 Daltons, 100 gram per mole. And then this is built up into a peptide, which has between 2 to 10 residues linked together by peptide bond. Two amino acids come together and a water molecule is eliminated to form a peptide, a dipeptide. And then that process can continue. And when you get above 10 residues, we have what's called a polypeptide. And these polypeptides can stay as one chain, or you can get more chains coming together, linking together either covalently or non-covalently. So proteins can have more than one chain or subunit. For example, hemoglobin has 4 subunits in its structure, which are non-covalently linked together. Polysaccharides, okay, these have different basic structures. This is a typical monosaccharide unit, this 6-membered carbon ring with an oxygen in there, and a side chain with another carbon, this time linked to this acidic group. So this is a monosaccharide, and monosaccharides, depending on what groups are coming off, can have a molecular mass, molecular weight of around 200 Daltons. For example, glucose has a molecular weight of 180 Daltons. These can link together, again with the elimination of water in a condensation reaction to give a disaccharide. The bond this time is not a peptide bond, but it's called a glycosidic bond, and the two molecules come together. So disaccharide, two residues. This can build up further to a oligosaccharide structure between 2 and 10 residues. Then when you get above 10 residues, you have a polysaccharide. So a typical polysaccharide has a molecular weight greater than 2,000 Daltons. Whereas a protein, typical protein has a molecular weight of greater than 1,000 Daltons. 1,000 Daltons is 1 kilodalton. Right, that's sort of the basics of molecular weight and how proteins and polysaccharides are macromolecules. Proteins and polysaccharides are very different. Proteins, generally speaking, are very precise monodispersed structures. They're coded by a gene. Okay, so the genetic template is there to code the production of a protein molecule, so that every time the protein is produced, it has the same molecular weight, the same numbers of amino acids, because this is what's been coded by the genetic template. So they're generally precise monodispersed. That means single molecular weight structures coded directly from a gene. And they're also usually, but not always, folded structures, folded regular structures with a fixed molecular weight. Because polysaccharides, their synthesis involves enzymes, like proteins synthesized by enzymes, polymerases and things. And although these enzymes themselves are precise structures, in the production of polysaccharides, the polysaccharide structures produced are not, because there's no genetic template involved in the synthesis of polysaccharides. So that means they are polydispersed. They have a distribution of molecular sizes. And generally speaking, the poorly defined structures compared to compact protein molecules, although you can get some secondary structures, the formation of helices in polysaccharides. And then we get called glycopolymers, and the glycopolymers is a general term to represent polysaccharides and also glycoconjugates as well. And these glycoconjugates involve sugar and some other entity, some other molecule. So nucleic acids are glycopolymers because they involve conjugation of sugar, ribose, deoxyribose, or whatever, with nucleotides. Mucin glycoproteins, these are glycoconjugates. These basically have a protein backbone with sugar molecules coming off. Mucins are the molecules which coat our alimentary tract. Just wait 1 second, I can't. This full screen. Let's just go. Okay, I'm trying to arrange things so I can actually see you guys on my screen. All I can see at the moment is right. Have you still got a full screen? What can you see? You still got a full screen, folks?
Yeah, we have got a screen with like it's blank on the background. the
Okay, you can see the slides on the left-hand side here.
yeah.
So that's fine. You can't see me or anybody else, can you?
No.
Actually, I can.
Yeah, me too.
You can see me.
Yeah, I can see.
Yeah.
All right, that's good. Right, I think we'll continue with this because if I go full screen, I can't see you guys, so I've got no interaction with you. So if you're happy with this, can you read that slide okay?
Yeah.
Great. Right, so yeah, these glycoconjugates are conjugates of sugar or carbohydrate with nucleotides to give nucleic acids, with proteins to give glycoproteins, such as mucin glycoproteins, which form part of the mucus, which lines your alimentary tract, your bronchial tract and things. It means that these mucin molecules are very viscous and jelly-like, and they provide protection for surfaces, epithelia. So if you have, an apple or orange or something, or buy a chocolate bar and eat it, it's the mucus, these glycoproteins, stops your epithelia from being very badly damaged as the food moves down the alimentary tract. It's like a lubrication protective layer. So these are very important molecules. There's membrane glycoproteins, which can be important in molecular recognition and signaling phenomena. Proteoglycans, these form part of connective tissue, complexes of polysaccharide and protein. And immunoglobulins, antibody molecules, these are also glycoproteins because they're protein with sugar attached. So sugar plays a very important role in biology and in life, not just by itself, but when it's conjugated to other molecules. And we represent this amount of sugar on a molecule, which is covalently attached, by what's called the degree of glycosylation. So ovalbumin, anyone know where ovalbumin comes from? Okay, ovalbumin comes from eggs, ovalbumin. So it's basically egg protein. It's the main protein in eggs. Not a glycoprotein. It's got a small amount, 5% of sugar attached to it, whereas a mucin glycoprotein has much more sugar. 80% of the molecule is sugar. And these molecules are also polydispersed. That means they have a spread of molecular weight because when you've got lots of sugar around, there's no genetic template to control the size, so they have a huge spread of sizes. And for a long time, these glycopolymers, these polysaccharides and things, used to be regarded as what's called the Cinderella macromolecules of biochemistry. Hang Zhou, Xing Zi, I think, do you know who Cinderella is?
No, I didn't know this.
Yeah, Cinderella
yeah.
is some sort of girl or something, like
Fairy
a girl
tale.
in a fairy tale.
Yeah, it's a fairy tale, and Cinderella
Not fairy tale, yeah. But
has two from Germany. She has two ugly sisters.
yeah.
She's always forced to do all the hard work and things. She's the one that's forgotten about. And the same with biochemistry for many years, that polysaccharides and glycopolymers, with the exception of nucleic acids, were always regarded as the Cinderella molecules of biochemistry, compared to the big ugly sisters who got all the attention, that was proteins and nucleic acids. But people realize now, or have done for many years, how important sugar is, not just in terms of food and everything else, but in terms of the role that sugar molecules play in molecular recognition phenomena, including all the bugs that live in soils, Hangzhou and Zizang. Yeah,
yeah, it's hard to
they're
pronounce
important
it.
Molecules in environmental science as well as in other aspects of biology. So, because of this recognition, they are no longer regarded as the Cinderella macromolecules. So, if you hear the term Cinderella macromolecule, you know it's referring to sugar or polymers which have sugar on it. Right, now we keep on these sugar molecules for the moment because they are quite interesting. And they come in all shapes and sizes, these polysaccharides and glycopolymers. So we can have sizes have a simple monosaccharide, that means 1 unit, which has a molecular weight of 180 or molar mass of 180 gram per mole. Then when the two molecules come together, you get a disaccharide like glucose or maltose, depending on how the bonds link up. So the molecular weight of sucrose, what's 2 times 180?
360.
360. So is this a mistake? 342? Why isn't the molecular weight of a disaccharide, 2 sugar molecules come together, 2 glucose molecules, 360?
They share the same bond. I don't know.
So when 2 molecules come together to form a glycosidic bond, a water molecule is released.
Oh,
Yeah, and a water molecule has a molecular weight of
18.
18. Yeah, that's good. Then you can get polysaccharides, much larger molecules, pectins, which come from jams and jellies. Also, you can get them in. So, well, you find them in jams and jellies. That's not where they come from originally. They come from the cell walls of fruits like tomatoes, apples, pectins, and some of these desert plants in China and all this. You can find pectin molecules. They have a molecular weight or molar mass of about 200,000 gram per mole. Alginates, which come from seaweeds, things, and you also find them certain bacteria, especially those which sadly come along with cystic fibrosis infections. These alginates again can have molecular weights, molar masses of about 200,000 gram per mole. Then you get some very large ones, guar, million. It's bacterial, so this microbial polysaccharide xanthan, 3 million. And then amylopectin, where do you find amylopectin, folks?
I don't actually know what it means, so.
Well, Thika might know. If you're working with Gleb, you should know might know what amylopectin is.
Yeah. Maybe.
Okay, it's an important molecule in starch. So starch.
Yeah.
You know, we all eat starch, rice,
Yeah.
everything.
Yeah.
In rice, you've got 2 molecules, or rice. You've got amylopectin and amylose. These are the molecules of starch.
Yeah.
So, I mean, Chinese like to eat lots of rice. Is that right? You have rice cookers and things. So Many of the Chinese friends I have got these rice cookers. So rice is full of amylopectin. Zhang, okay?
Yeah.
Okay.
Kind of see what it means.
You eat it every day. That's a huge molecule, amylopectin, 50 million molecular weight. And these are some of the complex shapes you get. So huge range of sizes, a huge range of shapes. You get these compact structures like amylopectin. You get flopsy molecules like dextrans. You get sort of more stiffy shaped molecules, arginates and pectins like that, because they're very negatively charged, so they repel a lot. Chitosans, anyone know where chitosan comes from?
Yeah, the shell of seashells and all.
That's right, crabs,
Crabs,
lobsters.
yeah.
Yeah. You eat lots of crabs and lobsters, guys?
Sometimes.
Okay. Well, on the
Yes.
shells, the hard shell, that's its molecule called, it's chitin is the molecule, but then you can treat the chitin with alkali to give a molecule called chitosan, which can dissolve in watery solutions. And these chitosans have sort of flexible types of shapes. You can get dimers as well, where two molecules come together to form a dimer. And xanthan is a dimer. Carrageenan also, which comes from seaweed as well. And there's some debate whether xanthan forms a double helical conformation. But so you get, think about polysaccharides is they come in all sizes and shapes, and they're polydispersed. That means they're very broad in the molecular weights. So very different from proteins, which are more often than not compact, regular structures with a defined molecular weight. Right. This is an important point before we go on, just in case you want to go complaining to the Vice Chancellor or the President of the System International, complaining that some Nottingham scientists are not using SI units. SI is the now universal accepted units for measurement, and we conform to that whilst we can. But it's not always convenient to do so. And sometimes it's more convenient to work in centimeters, grams, and seconds rather than meters, kilograms, and seconds. For example, in a laboratory, we're dealing with small amounts of solutions and things, centimeter cubes. We're not dealing with meter cubes, which is huge. And we're dealing with grams, sometimes milligrams of material, not kilograms. So if we're dealing in a laboratory situation with solutions of molecules and things, we tend not to use SI units. We use what's called centimeter, gram, second units, centimeters, grams, and seconds. It's just more convenient. And sometimes we work in milligrams, where a milligram is a millionth of a gram. And the other thing is, you've got to ask yourself about the units of molecular weight and molar mass. What's the molecular weight of water again?
18.
Right, 18 Daltons. You see that? How clear is that screen, folks? Is it bad or good?
Yeah, it's good.
See it now?
Yeah.
18 Daltons, 18 grams per mole. All right? But gram is not an SI unit. It should be kilogram. So the molar mass of water in SI units is actually 18 kilogram per mole. So 18. Oops. 18 times 10 to the minus 3
Yeah.
kilogram per mole. All right, so that's not numerically equivalent to the molecular weight or molecular mass in Daltons. And in biology, biochemistry, nobody refers to the molecular weight of water as 18 times 10 to the minus 3. Very few people do. It's always 18. And that's the CGS system, not the SI system. The chemists like to use this kilogram per mole, but not generally biologists. We like the CGS units, so that's 18. So that's why we use CGS. Not always, and we'll see in a minute when we talk about energy and things. We actually prefer to use the SI unit of energy. What's the SI unit of energy, folks?
Joule.
Joules.
A joule.
Okay, and the CGS unit of energy is called the erg.
Yeah.
Very few people have heard of that. Okay, so before we have a break, I just want to, well, yeah, these are the various conversion factors between units that you need to be familiar with. So kilogram, SI, CGS is a gram. 1 gram is 10 to the minus 3 kilograms. Volume, SI is meter cubed. In CGS, it's centimeter cubes or a milliliter. Milliliter is the same as a centimeter cubed. And 1 centimeter cubed or 1 mil is 1 times 10 to the minus 6 meter cubed. And you know, when you're converting from one to the other, make sure you get the powers of 6 right, because if you multiply instead of divide, you can get huge errors. So make sure you get your conversions correct. And same with concentrations, kilogram meter cube, we don't use that. It's grams per mil, grams per centimeter cubed. Densities, molar mass, just done that with water. That's the conversion. And then with energy, we use joules, but if you want to use CGS units, then the erg is 1 times 10 to the minus 7 joules. And we'll see in a minute, we sometimes use joules per mole or ergs per mole. And if you're in an examination situation, which you're not now with the course, then you're given full conversion details. So that's just why we use CGS units and the conversions between them when handling molecules, solutions of molecules. Although when dealing with energies, we still stick with joules. Right, guys, can I carry on for 10 minutes before we have a break? Is that okay?
Mm-hmm.
Is that fairly easy to understand? Was that pretty basic?
Yeah.
Right. So that's molecular weight and different types of macromolecules and how they're built up into macromolecules. And a bit about polysaccharide size and shape. We'll do proteins next week. And why we use CGS units. Now, the next basic thing we have to just introduce is the free energy equation. And this is such an important equation in biology, I guess in environmental science, because it tells us whether something's going to happen or not, or at least happen by itself without the help of something else coming in to make that reaction occur. So it dictates whether a protein is folded or unfolded, a polysaccharide folded or unfolded, whether molecules interact with each other or whether they stay apart, whether a molecule will dissolve in a liquid or whether it won't, it'll stay dry. All this is governed by the free energy equation, which comes from the second law of thermodynamics. It's a form of the second law of thermodynamics, which tells us if a reaction will proceed or not. And it's this equation here. The change in free energy, energy that's available to take part in a reaction, equals delta H minus T delta S, where there we are. Delta G is the free energy change, units joules per mole, and G is the free energy, the energy available to take part in a reaction, and delta means change, so change in G. And by free energy, we don't mean the nuclear energy in the molecule, the atoms and things. We're not involved in any nuclear reactions here. We're just involved with reactions between molecules or involving molecules, whether they fold or stay apart, or whether they dissolve or don't dissolve, or they interact or don't interact. It's the free energy of a reaction, the measure of the energy available to take part in a reaction. Delta H is the enthalpy, or the heat energy at constant pressure. And delta H is the enthalpy change, or heat energy change at constant pressure. Again, the units are joules per mole. And T is the temperature in degrees Kelvin, where not degrees centigrade, degrees Kelvin. So 0 degrees is 273 degrees Kelvin. And delta S is the entropy change, or change in randomness of a system, how random a system is. Delta S is the change in that randomness. And the units are joules per mole per K. So just a question to all of you, have you met this equation before?
Yes.
Yes.
Okay. In the first year, maybe, Cezanne?
Yeah, I've seen it before.
All right. So it's a very important equation in biology, of course, in chemistry. And basically, the second law of thermodynamics is that for a reaction to be spontaneous or proceed of its own accord, the free energy is minimized. So a system doesn't like energy to be around. It wants to get rid of it if it can. And for a reaction to be spontaneous, the free energy G has to be, or free energy change has to be negative, so that the total free energy is minimized. So a reaction will proceed so that free energy is lost. So if free energy is lost, the change in free energy has to be positive or negative if it's losing stuff. Negative. Okay. So for reaction to proceed, then the free energy change must be negative. and the reaction will proceed until the free energy is a minimum. Let's say you have a molecule A which converts to a form B. So if everything is A, then that's the free energy. If everything is B, if that's the free energy. But that clearly is not the minimum in the energy. So A or B will come to some sort of equilibrium of the two states so that the free energy is minimized. So in this direction, the change in free energy is negative, and in this direction, the change in free energy is also negative until we get to equilibrium. And the condition for equilibrium is that equilibrium, there's no further change in free energy, delta G equals 0. So that's all free energy is. It has two components, one due to the heat energy at constant pressure, H, what we call it the heat energy enthalpy, yeah, and the entropy, the degree of randomness of the molecule. So reaction will proceed, so it becomes more random. That's good, because as delta S increases, that becomes more negative. Or it'll proceed so that heat energy is given out. So if delta H is negative, that means heat energy is given out. It can also proceed. And sometimes, as long as the overall delta G is negative, then a reaction will happen. So when a protein folds, it becomes more ordered, which is not favorable, because delta S is negative, because it loses randomness, and negative times negative is positive. And that gives a positive free energy. So protein folding should be unfavorable because it becomes more ordered and therefore positive free energy change. Unless when the protein folds, lots of favorable bonds are formed, hydrogen bonds or electrostatic bonds, resulting in a release of heat energy. And so long as that delta H term is more negative, then this lot is positive, then the protein folding reaction will occur. That's just one example of why this equation is important in telling us whether a reaction will occur or solubility. That's right. A typographical mistake there. All right, folks. So I think we can have a break now, if you like, for 10 minutes or so. Does that sound pretty straightforward so far?
Yes.
Yeah.
Hang Zhao, you okay with that?
Yeah.
Design?
Yeah.
Latika, that should be pretty familiar. That's easy. Right. So we can now press on after the break. Now we got that basic stuff out of the way. And I think there may be an assessed question actually, guys, just to check that you understand that relation. And I'll show you that at the end. Good. Let's have a 10-minute break now. We'll reconvene at 11:30, and then we'll go on to the next topic, which is macromolecular shape. So I will end the record now.